In this video, we are going to learn how to evaluate triple integrals using spherical coordinates. So let's say that I have a triple integral of my function f of x comma y comma z over some three-dimensional region. And I want to do this using spherical coordinates. So we've seen that we have these equations for what x, y, and z equal using spherical coordinates. We saw these in the last video. And that when we do a change of coordinates, I need to calculate the Jacobian. So in this case, because I have three new variables, I'll have this 3 by 3 matrix that consists of the partial derivatives of this, which I've already worked out. And once you do the determinant, I have worked out a bunch of those algebra steps. And let's just do this last bit of simplification. At this last step, I notice that there's a sine phi for both of these terms. So I'm going to factor that out as well as the negative signs. And that leaves me with cosine squared phi from the first term, cosine squared phi, and then plus sine squared phi. But cosine squared plus sine squared, that is just equal to 1. So that leaves me with negative rho squared times sine of phi. And when I use this Jacobian in my new formula, my new triple integral, I have to take its absolute value. And the absolute value will get rid of the negative sign. And then I need to think about, well, are each of these other things non-negative or are they negative? I know rho squared is not negative. For sine of phi, remember in spherical, phi is in between, it's on the interval 0 to pi. And on that interval, sine of phi is non-negative. So that's non-negative, rho squared is non-negative. So the absolute value will get rid of the negative, and then this remaining portion is non-negative. So I can just write it. I'll get rho squared sine of phi. I don't need an absolute value around that because it's already non-negative. So my triple integral becomes this new triple integral where what this notation means is just change this original function to spherical coordinates. And then we'll multiply that by the absolute value of the Jacobian. And that's our rho squared times sine of phi. And then I'll have my new variables, d rho, d phi, and d theta. Okay, so how do we set up these new limits of integration? Well, in spherical coordinates, we're pretty much always going to do it in this order. D rho inside, and then d phi and d theta. I know there's a lot written here, but let's break down what this is saying with an example. So my example says find the volume of a sphere with the radius r using triple integrals. Okay, so I'm going to start by drawing a picture. So I will draw my axes. So my z-axis, my x-axis, x-axis, and y-axis. So let's draw these axes. And then I'm going to go ahead and draw a sphere. So sphere of radius r. It doesn't say where to draw it necessarily, so I'll just make it centered at the origin for simplicity. So these intercepts are all going to be capital R. Capital R, capital R, capital R. And to make it look a bit more 3D, let me draw the equator. I'll draw one of these circular cross sections. Okay, so a sphere. Okay, so we might recall from geometry that the volume of a sphere is 4/3 pi capital R cubed. So we're going to prove that using triple integrals. Okay, so volume, when I use a triple integral, will be the triple integral over this region, I'm going to call it d, of the function 1. And then I write dv. So I'm now going to be converting this thing to spherical. And the reason why is a sphere has a very simple equation in spherical coordinates. For this sphere, its equation is just going to be rho, which represents the distance from a point to the origin. Well, no matter what point that I take, that distance is always just capital R. So the equation is just rho equals capital R. And that's just much simpler than our normal x squared plus y squared plus z squared equals r squared. Okay, so that is why I want to switch this to spherical. Okay, so that'll give me a new triple integral. I'm going to leave some space for each of these for the limits of integration, where I got to convert this equation to spherical coordinates, but there's nothing to convert. This is just a constant. It just stays as it is. And then I multiply by the absolute value of my Jacobian, which is rho squared times sine of phi. And then I'll get my new variables, which are, I'll have d rho, d phi, and d theta. So how do we find these limits of integration? So the inner variable is d rho. So I need to know what rho equals here and what rho equals there. And the way I do this is I'm going to draw an arrow radially outwards from the origin out of my region. So maybe it kind of bursts out from the surface at some point on the edge of the sphere. And where it enters the region, which actually is right away, that's the lower limit of integration. So right away at the origin, rho just equals 0. And then where it exits, that equation's rho equals capital R. That's my upper limit of integration. Okay. Next up, I need the limits of integration for phi. So for phi, remember phi is the angle between, if I look at the positive z-axis and some point, and I make that line, phi is this angle. So when phi is 0, I'm just looking straight on the positive z-axis. And I can visualize this as, okay, imagine this is a laser pointing straight up. And if I increase that angle, I start to go away from the positive z-axis. How far do I keep going before I kind of reach the edge? And how far I would go for this one, it actually is all the way to the bottom. All the way to the bottom, and that's when phi equals pi. So it turns out that phi goes from 0 until pi, all the way from the top to the bottom. And you might wonder, wait, like, why don't we go past pi? Because don't I want to get to spots like this on the circle, on the sphere? Well, I can reach this point if instead I took an angle to this spot and I just use theta to rotate this point around the sphere to that other side. That's why I only need to go until pi. Okay, and then finally I need the limits of integration for theta. So for theta, it's similar to what I do for cylindrical coordinates. You look at the shadow of the region on the xy plane. So the shadow on the xy plane. So I'll draw my xy plane. And that's based on kind of how wide does the sphere get. And that's the widest point is at this equator here. That circle, let's draw that. So I'll draw that circle. The radius is capital R. And if I look at that, well, to go all the way around the circle, theta has to go from 0 to 2 pi. So those are my limits of integration for theta. 0 to 2 pi. Theta equals 2 pi. Okay, nice. So I have the integral. I'm ready to evaluate this. So, okay, one of the things I notice about this is all these limits of integration are constant here. And this function can be split up into a product of a part that just has rho, a part that just has phi, and there's nothing with theta, so I can think of this 1 as being the part with theta. So I can decouple this integral. So I'll get the integral with theta, which goes from 0 to 2 pi, of the function 1 d theta. So that'll multiply the phi integral, 0 to pi of sine of phi, d phi. And that'll multiply the rho integral. So from 0 to capital R of rho squared d, oh, sorry, let's write that better, d rho. Okay, so with this first integral, I'm going to trust that we can work this out. And if you do that, you'll get 2 pi. For that next integral, the antiderivative is negative cosine of phi. And then I have to plug in the 0 and the pi. The last integral is going to be rho cubed over 3. And then I got to plug in 0 and capital R. So when I plug in and subtract, I'll get 2 pi first. This next portion becomes 2. And the last term becomes r cubed over 3. And if we multiply this out, this becomes 4/3 pi capital R cubed. And that's what we wanted. We've actually just proved the formula for the volume of a cube. So in the next video, we are going to do another example where we use triple integrals with spherical coordinates.